Welcome, everyone. Thank you for coming to my session. Hello. For those of you I haven't had a chance to meet yet, my name is Kris Howard, and I am a Solutions Architect Manager at AWS, Amazon Web Services, in Sydney, Australia. I traveled a very long way to be here. You can tell from my accent, I didn't grow up there, though. I did grow up in the US. I've been living in Australia for about 20 years now. But this is my very first ever visit to Lithuania. And to Vilnius, of course. And I was particularly excited about one thing: to visit your amazing local knitting shops. I don't know if you've been here. This was me on Tuesday this week at Mezgimo Zona. I hope I've said that correctly. Yeah, which I think stands for the knitting zone. So I geeked out hard in there. I was very excited to see the local yarns. I came away with a big cone of linen. Apparently, Lithuania is very well known for its linen, so I'm taking some linen home with me and some beautiful Estonian wool as well. You see, I am actually a knitter. I have won prizes for my knitting in Australia. You may have even seen me knitting at the sessions. I was knitting in here before the talk just to calm my nerves down a little bit. But I am also a geek. I have been working in the tech industry for more than 20 years now. I started off my career as a front-end developer. I was a business analyst, I was a project manager, and eventually now a people manager. And the thing that I really love is to combine my two passions together. So a few years ago, I wrote a talk on how knitting patterns are like a computer programming language. You know, they have for loops, and they have while loops, and they have switch statements. And I gave that talk more than 20 times, all around Australia and Asia, at events like TEDx Melbourne, at big tech conferences like this one, at local meetup groups. I even gave it at the New South Wales Knitters Guild camp. And I thought after all that, I've got the knitting and programming bug out of my system, finally. But that clearly wasn't true, because here I am on stage at a tech conference talking about sticks and string again. Now, this talk is kind of the spiritual sequel, call it, to that earlier talk. There have been some really cool breakthroughs in the field, believe it or not, in the last few years. I want to share them with you, and I also want to tell you about a little project I've been working on, a little machine learning project that, you know, not to set expectations too high, but has the potential to disrupt a 1,500-year-old industry. So, you know, no biggie. I'm going to begin, though, by just giving you a little bit of a recap on why I think computers and technology and programming go so well together. How many of you in this room have ever learned to knit? Right? So the knitters know that there are actually only two stitches, knit and purl, and you combine them in different ways. So if you think about it, knitting is inherently binary. And to geeks like us, that means we can use it to embed data in really interesting ways. In fact, at a very basic level, I can knit a digital file by just using knits as the ones and purls as the zeros. This is an example. This scarf is the source code to Ravelry.com. Now, Ravelry, for those of you who don't know it, is like GitHub for knitters. Okay, it's a massive repository of knitting patterns, yarns, and projects, but it's also a social network, and it's got forums. So this knitter, Carrie Ann, converted the HTML of the homepage of Ravelry into binary and then knitted it into a scarf using the method I just described. Now, if you're more of a black hat type, you could even knit a virus this way. In 2001, a team of activists at the Viral Knitting Project did just that. They knitted the source code to the code red computer virus into a fluffy red scarf. No firewalls picking that one up. In fact, the scarf I am wearing right now is malware. It's from an artist named Jeff Donaldson, who goes by the name Glitch House, and he's created a line of accessories and homewares that he calls malware, get it? Which encode famous malware, right? So I backed his Kickstarter, and so this scarf is actually the I Love You virus, which those of you who are old will remember knocked out like half the internet in 2000. Yep, been there. But you know, let's say you need something to go on the back of the couch, you can get Stuxnet as a throw. Now Jeff, as you can tell, he uses color to encode digital files in his knitting. Another way that you could use color would be to vary the width of knitted stripes to encode a character set. The stripes on this guy's jumper, Adam Knits, that's his name, the stripes on his jumper actually spell out the classic first programming exercise, hello world. I myself used color to design a pair of QR code mittens. These did win me a prize. Now these were really difficult to get to work, I'll be honest with you, mostly because QR codes really rely on everything being quite square, and knitted stitches are usually wider than they are tall. So I went through a lot of failed prototypes to get something that worked. I figured out that the technical solution was to stretch the hell out of it, okay? So I got one that actually does scan. You can try it out later. I don't know if it'll work from the photo so well. But it does work, and it points to a URL that has the pattern for the mittens. So they're self-replicating. Okay, now, a new field that's gotten a lot of attention in the last few years is data art or information art, and that can also be knitted. In 2018, you might have seen this on the news, a German woman named Claudia Weber, she knitted a scarf that tracked the train delays on her daily commute. Every day she'd add 2 rows. She'd add gray for delays of under 5 minutes, pink for delays up to half an hour, and red for delays over half an hour. And as you can see, Claudia had a very bad stretch there. And this scarf went viral online, and it got sold off on eBay to raise money for a charity in Germany that benefits people at train stations. Another group of knitters have created the Tempestry Project, which is an effort to assist climate change discussions by taking the problem and making it something beautiful and tangible and accurate. So each tempestry, that's what they call these, it represents the daily high temperature over the course of a year in a given location, with January at the bottom and December at the top, all using a consistent yarn colors and temperature range. And the website, the Tempestry website, actually has instructions. If you want to make one of these of your own, you can even get a kit to do it. Another project that went viral, which I really love, is Seung Lee's sleep blanket. This documents the first year of his baby son's sleep patterns. So he used an app to manually track the baby's sleep patterns, and then he used Python and JavaScript to turn that into a visualization. He built a web app so that he could track his progress on the pattern because he was knitting this thing all over the place. It consists of 185,000 stitches. It took him 3 months to complete. And every row represents a single day in the baby's life, with the top row being the day the baby was born, and the bottom row being the first birthday. And every stitch represents 6 minutes of time, either awake in gray or asleep in blue. Isn't that very lovely? Now, another visualization that I really like is the Neuro Knitting Project. So this was fun. The creators plotted brainwaves and knitted them into an accessory. So they used a wearable EEG to record users' affective brain states while listening to a piece of music, Bach's Goldberg variations, and they knitted that then on a hack knitting machine. Very cool. Yes, hack knitting machines are a thing. Let's talk about those for a minute. Knitting machines have been around for a really long time, but hacking them has only gotten popular in the last few years. So some of the earliest ones actually used punch cards to input patterns. I've still seen those in use, in fact. But then they had ones that were computerized, and they had like hundreds of stitches built in, and you'd sort of pick them with a really, little UI. Some of them had a floppy drive or a special cable for transferring your designs. So hacking them usually involves buying one of the old ones, making your own serial cable, and then writing software to transfer new custom designs to the machine. There's even an open hardware project called Knittic, where you use an Arduino as the new electronic brain for the machine, which allows you to do cool stuff and actually send new designs on the fly. And my friend Sarah Spencer, she's a hacker, a developer, and a textile artist working in Melbourne, Australia. This is her machine. She turned a dumb 1980s knitting machine into a wireless networked knitting printer, okay? Using Python, using custom hardware that she designed and 3D printed herself with her partner. So that on the front is actually a custom color changer that she designed and built. And she's built some really amazing, used this to make some really amazing artworks, and she's given tech talks about them online as well. So if you look up Heart of Pluto, that's her website, you can see some of those. Not everybody's a hacker though, but people still want knitting machines. So in 2017, Knitterate launched on Kickstarter. So Knitterate was the goal was to bring easy-to-use professional knitting machines to everyone, because there are industrial knitting machines that they use in garment production. Those suckers cost like $50,000 US, versus the Knitterate machine is actually only selling for $7,500. So manufacturing just began this year, and I believe they've just started shipping. So I'm really keen to see what effect this has on clothing production. I have not myself ordered one. My husband's here. I'm sorry, honey, I did not order one, mainly because they're really big, and I think our house is too small for them. Now, one of the challenges for the Knitterate creators and for anyone who's trying to build a computerized knitting machine is how you actually send your knitting patterns to it, how knitting patterns are expressed and specified. There's no off-the-shelf software that does this. And it turns out that what you really need is a domain-specific language. In order for knitting patterns to be shared and reused without having to be rewritten every time, designers need a standard way of expressing the algorithm, of expressing the steps and operations that can be understood by both humans and machines. Now, one of the very oldest ones, and some of you are probably aware, are the punch cards that were used on the Jacquard loom back in 1798. So Jacquard invented this loom and developed a system where punched cards would control a series of operations that the loom was supposed to carry out. Now, 40 years later, Charles Babbage wrote of, hey, maybe that would be something I could use to put programs and data into my analytical engine, right? So yes, weavers had it first. And as I mentioned, punch cards were still being used on knitting machines well into the 20th century. Now, this is probably the format you're most familiar with knitting patterns, is text expression. Definitely the most common. But I hate to tell you non-knitters this, there is no standard way of writing these. Every single designer does it completely differently. You see, this pattern has to spend quite a bit of space just explaining what the abbreviations mean. I can't just take a pattern like this and give it to someone else and expect them to be able to execute it. It's kind of like assembly code in that way. Now, you may have also seen knitting graphs. These are often accompanying text patterns, especially when they're really complicated. So graphs are a symbolic expression of the pattern. They tend to be more concise. There is still no standard for them, but the symbols used here are pretty widely used. And the cool thing is they kind of look like what they represent. So like those O's, that makes a yarn over, which makes a hole in the knitting, like when you're knitting lace. And that sort of chicken foot looking thing there, that's a decrease that makes 3 stitches and takes them down into 1. So overall, this abstraction is really concise. Between the colors and the symbols, you've got like 9 pieces of information in a really small space, which is good. But that orthogonal grid is kind of rigid. And some knitters think we could do more if we had a visualization that represented knitting patterns more accurately. Enter stitch maps. So stitch maps are a knitting pattern visualization that let you see how parts of a stitch pattern interact. So not just the sequence of stitches in a given row, but how they interact over time from row to row. So with decreases and increases, you actually see what effect that has on the shape of the knitting. This particular pattern is called feather and fan, and it results in a wavy piece, like you see here. Now, the super cool thing is that stitch maps are actually compiled from a domain-specific language called Knitspeak. So if you go to the Stitch Maps website, you enter your pattern in Knitspeak like this. So this is Knitspeak. It looks kind of like a normal knitting pattern. And you hit compile, and it will turn that into a visualization that looks like this. And this gives you a much better idea of what the fabric will look like and even sort of how it'll behave. There are also industrial knitting DSLs. I mentioned industrial machines. Well, you have to actually program them. Shimaseki is a company in Japan. They make some. There's a screenshot of their software. You see here, they've specified the pattern on the right using both symbols and colors to encode what the actions of the machine will be. And on the left is actually a simulation of what the knitted fabric will look like. This is another one. This is the software for a Stoll knitting machine. This is serious stuff. Patterns are essentially implemented in machine code that can be simulated and then fed directly into knitting machines. I'm told that when you buy one of these big machines, you actually fly to the factory for several weeks to learn how to use it. There are also some fun niche knitting DSLs. It seems to be a really fun project for computer science students who are also knitters to write their own knitting pattern language and build a compiler for it. So here's just one that I found. It's called Pearl. This is a domain-specific language that Chelsea Corvus wrote for a compiler's course in 2016. And it uses notation similar to traditional knitting patterns, but sort of adds some syntactic sugar, to allow them to be verifiable and to make them a bit more modular and reusable. And the cool thing is she has a tool on her website that actually demonstrates it. So you see here on the left is a pattern that's actually written in Perl. It's the bit at the top looks like a knitting pattern, but below that it looks a little bit more like a computer program. And so once you hit the compile button, it actually turns that into the traditional knitting pattern on the right. So her version is more concise, but it has the added advantage that if I wanted to change the size of the piece, I could tweak some of those variables and then compile a totally new version of the pattern without having to go in and work out all the math myself. Now, one of the more serious attempts to open source a knitting DSL was KnitML. People always laugh at that one. It is a thing, KnitML. It was launched as an open source project in 2007 based on a vision to create a standard markup language for knitting patterns. So the creator, Laura Porter, noticed patterns are written all different ways. There's no standard. It's difficult to convey meaning universally. So the goal of KnitML is to promote a new international standard, an intermediate format for knitting pattern expression. It only expresses the contents of the pattern, so the steps you need to go through to make the knitted thing. It doesn't talk about how it's actually meant to be laid out. So this is what KnitML looks like. It's not particularly concise, and it doesn't look a lot like a traditional knitting pattern. But bear in mind, this is an intermediate format. This is for software pattern exchange and transformation. This is for computers. It's not expected that human beings would ever actually touch this stuff. Instead, the project creators provided a pattern authoring tool called Knitting EL, which stands for Knitting Expression Language. And this is supposed to be a simpler way for designers to express a knitting pattern, and it looks slightly more human readable. And so the project provides Java-based software to convert knitML patterns into Knitting EL patterns into knitML. Unfortunately, knitML has not been actively maintained for a few years, so I'm really hoping I can find some people here who'll help me revive it. But why? I see some of you probably asking yourself, Kris, what is the point of spending all this time formalizing the way knitting patterns of all things are, shouldn't we be focusing our efforts in quantum computing and stuff like that? Well, formalizing knitting patterns in this way allows for all sorts of really useful operations. Users could generate a custom pattern for just their size, just the thickness of yarn they're going to use. Yarn varies quite a bit, so it can really alter a knitting pattern. So similar to what we saw with Purl, you could change some numbers and spit out a whole new pattern. They could output charts or text, whichever the knitter preferred working from. They could use English or metric measurements, or even spit out a pattern in different languages. Crucially, it would also allow for unit testing. So many knitting patterns get published with errors in them. And there are actually some pretty strict rules about it. Like if a row has 20 loops in it, on the next row, you have to use every single one of those loops or the piece will unravel. So imagine that a designer could have a CI/CD pipeline that would actually check that their knitting pattern was correct and that all parts of it were knittable. Now, another really exciting application of knitting DSLs are simulators. We've seen how the industrial machines have these, but also here's an example of an open source knitting visualizer called Knitter that takes a knitML pattern and it produces a 3D model of the resulting knitted fabric. This one also hasn't been updated in a few years, so if you know C, please go help. Luckily, there are other people who've taken simulated knitting a lot farther. This is a paper that was presented at SIGGRAPH 2012. Now, SIGGRAPH is the big computer graphics conference. So as CGI characters have gotten more realistic in video games and in film, their clothes have gotten more sophisticated too. Now, the traditional way of creating clothing for a computer-generated actor is to just take a thin sheet and then just sort of apply a print to it, a texture to it. And that works fine for cloth, but it doesn't work great for knitting because knitting has a 3D structure. It moves differently, it looks differently under lighting, so it doesn't look especially realistic. So these computer scientists here came up with the idea of stitch meshes, this new concept, which is a mesh-based representation of knitted stitches that you can combine in different ways for CGI characters and can even be relaxed to look more realistic. So this is a selection of samples from the paper. So in each group of 3, on the left there is their stitch map, their stitch mesh, which uses color and shape to designate different stitch topologies. It's sort of almost like a little knitting graph. The middle is a computer-simulated image based on that stitch mesh. And on the right is actually a hand-knitted pattern built using it, hand-knitted swatch using that pattern. So you can see how close they've gotten. And in some of the cases, it is really close. This is a paper from 2018 called Knittable Stitch Meshes that builds on the earlier stitch mesh work. The authors of this one thought, well, if I can make really cool, realistic-looking knitting inside a computer, why not then turn that into a pattern that I can knit in real life? So they've built a 3D design interface, and I can go in there and design a really complex 3D shape, like say a teapot, and it will then generate the knitting pattern for me with minimal seaming. So it's not going to generate lots of little pieces that I have to sew together. They're going to be like, it's going to be as simple as possible. And this is really cool. This opens up a whole new world of 3D knitting design possibilities. But all these examples are done in a really smooth yarn. What about texture? So this paper, Nitpicking Textures, this was published just last month from the Carnegie Mellon Textiles Lab. So these scientists built a workflow that takes a knitspeak file, remember that was the domain-specific language from the stitch maps, and that compiles it into a knit graph, which is this directed graph they've created where nodes represent loops with yarn-wise and loop-to-loop edges. So they create this knit graph, and that allows for some really cool operations. So the paper provides a method for carving, which allows for resizing a piece of knitting while respecting texture. So imagine, if you will, you've got like a particular knitting pattern you like, which is like 50 stitches wide, but you want to knit something that's only 40 stitches. We can't just stop at stitch 40 because it might unravel or it's not going to look good. So what they've done is once you've converted that pattern into a knit graph inside a computer, it can actually work out the least essential stitches and remove them while keeping it looking the same. So you can actually shrink the pattern down to 40 stitches and then spit that out. They've also invented a method of patching, which allows you to combine knitted stitches of different textures into a piece that still stays the same shape. For those of you who've knitted, you know different types of knitting stitches, they pull in differently or they stretch differently. And if you combine them, like to make a square, it might not be square. They might pull in different ways. So this method that they've come up with, it has you increase stitches and decrease stitches so that you actually can combine the textures in a way that respects the shape. And then once you've done all these manipulations to the knit graph, you can actually output it back to a knitting pattern and knit it in real life. I bet you never realized how many computer science papers are about knitting. Okay, so this kind of all blew my mind. So just to recap, I can go from a symbolic representation of a knitting pattern, an expression of a knitting pattern. I can simulate the physical object inside a computer that it will look like. And then I can take that simulation and I can do things. I can manipulate it, I can change it, and then I can output that into knitting pattern that I can knit in real life and have the physical object. What about the reverse? Could we go the other direction? So this, could a computer read knitting, is the question that has been rattling around my mind for the last few years. So let me explain now what I mean by reading knitting. So this is a photo I took of my colleague Mega's jumper in our work kitchen back in August. I hadn't seen this particular jumper before that was really pretty, so being a knitting geek, I took a photo. And I can tell you, having never seen this stitch, that the background there is reverse stockinette stitch. I can tell you that if I zoom in, the diagonal lines, those are made up of 3 knit stitches that use a combination of decreases on one side and increases on the other to lean to the left and the right. Some of that I get because I can recognize the texture, and others I get because I can actually zoom in, a knitter can zoom in and read it, stitch by stitch, like deciphering cursive handwriting. Now this, my friends, is reverse engineering. This is taking a human-made object and studying it to deconstruct its design and architecture. Now, we use this a lot in software engineering. Everybody's heard this. But it turns out it's actually something that knitters are really big geeks about. They love doing it. This is a project from 2009. A knitter was browsing a website called the Shetland Museum Photographic Archive from the Shetland Islands up in the north of England, north of Scotland. And she found a photo of a lace shawl that was taken in the 1890s. So just a photograph from more than 100 years ago. And she posted on Ravelry, as I mentioned, and she said, hey, does anybody recognize the border on this shawl? I think it's kind of pretty. I might like to use it. Eventually, a mammoth project kicked off involving more than 30 knitters from around the world, spending hundreds of hours patiently trying to reverse engineer this shawl through trial and error. They got in touch with the museum to try and find out anything about the family who designed this. The Shetland Islands are really remote. There's not a lot known about it. But they eventually actually managed to recreate the pattern, and they made it available for free under a Creative Commons license. So if any of you want to knit it, please go on. You can go online, you can do it. But as one of the people in the project said, think of it, a piece knitted before the turn of the last century, designed by a close group of family and friends in an isolated area, preserved in a photograph, being recreated by a far-flung band brought together by technology and a love of this craft. Because you see, a lot of older knitting patterns, they just weren't written down. So reverse engineering, or forensic knitting as it's sometimes called, this can be a way of preserving really important history. This one might make me cry. So in 2003, a knitter named Leah Stern visited the US Holocaust Memorial Museum in Washington, DC, and she saw a little green sweater. It was knitted for 5-year-old Christina Chigger by her grandmother in 1941. In 1943, when Christina was 7, she and her family were forced to hide in the sewers in Poland for 14 months to escape Nazi persecution. This sweater was one of her most cherished possessions. It was one of the few things she was able to take with her during this ordeal. And she did survive, and she eventually, when she got to the United States, donated it to the museum. And so when Leah Stern saw this jumper, she felt she had a duty to reverse engineer the pattern to keep its history alive. She was able to examine the original sweater closely, take photographs, take measurements. That stitch pattern she was unable to find in any known extant stitch dictionary. It might be that Christina's grandmother just made it up. But she was able, through her research, to recreate it. And in 2014, Stern was able to present the finished recreation back to now Dr. Christine Chigger Karen, now an old woman, who picked it up and said, now I have my sweater back. And you can buy this pattern through Ravelry or in hard copy of the Holocaust Museum. I just think that's lovely. Oh. I didn't do it. But this is a fun one. This one I love. This is a pattern from my own collection. This is Sir Douglas Mawson, who was one of Australia's most famous Antarctic explorers. And this photograph was actually on our $100 bill for like a really long time. His balaclava, that's the thing that he's wearing on his head, it's been preserved by the South Australian Museum. And in 2014, master knitter Leanne Gould was able to recreate it. They published the pattern, and you can actually knit it yourself. And frankly, given how cold Vilnius is in November, I was kind of tempted to knit it before I got here. So, okay, if a skilled knitter can reverse engineer a pattern from a finished knitted item or even just a photograph of a finished knitted item, well, I ought to be able to teach a computer to do that, right? Like, that's what I was thinking. I should set some expectations here. Before I began this project, my knowledge of machine learning was zero. It was pretty much just XKCD cartoons. But fortunately, I work at Amazon Web Services, and we have a lot of really smart people who are very generous, some lovely colleagues. So I took one of them, she's like a machine learning PhD. I took her to lunch, and I said, okay, so I've got this idea, this great idea. Here's what I want to do. I want to teach a computer to read knitting patterns. And she goes, oh, cool. Someone's just done that, And I went, well, crap. All right. She sent me the paper. This is it. Neural inverse knitting, from images to manufacturing instructions. This was presented at the International Conference on Machine Learning just this past June. And the goal of these researchers was to take a photograph of a knitted swatch, and by swatch, I just mean a piece of knitting. Take a photograph of a knitted swatch, reverse engineer the pattern, feed that into a knitting machine, and then knit it an identical swatch. Basically build a knitting machine duplicator, okay? So they recognized pretty early on in the project that photographing knitting just kind of sucks for computer vision, okay? Because knitting is stretchy, it's floppy, it's often fuzzy, and so it's really hard to get a good image that you can actually train a model on. So the real breakthrough they had was they used both real knitted swatches and photographs, but they augmented that data with simulated data from one of those really expensive industrial knitting machines. And they figured out that training a machine learning model on both the real photographs and on simulated data gave a much better result. Now this paper, I'm not gonna lie, has a lot of calculus in it, most of which went way over my head. But from what I could tell from the results table, they haven't quite cracked it yet, but they're getting close. They're getting like more than 80%, frankly, accuracy, which is amazing, using both convolutional and generative adversarial neural networks. So I read all this, and I'm thinking, okay, so some really smart people who have PhDs, who are using all the math and all the science, they're still not able to crack this, so what hope am I gonna have? But rather than feel daunted, I decided I kind of found it exhilarating. Like, there's no way that I'm gonna be the one to crack this, so the pressure's off, right? I can just I can have a bit of fun, I can learn something, somebody's gonna crack this, it's extremely unlikely to be me, and that's cool. So with that in mind, I cut my scope way back. So rather than trying to read knitting stitch by stitch from a photograph, I decided to approach it as an image classification problem. So similar to how I did with Mega's jumper, where I could recognize that texture was reverse stockinette stitch, I wanted to use that sort of approach where I'd have an image as input and it would output a class, which was a type of stitch. So this is the plan as I saw it. Get some training data, how hard would that be? Label it, build a model, deploy it, build some front end, and then, dance on the grave of the knitting industry. Sounds like a good plan, right? All right, easy peasy. Step one, get training data. The first thing any machine learning expert will tell you is this where you spend most of your time. This is the hardest part. Getting clean data is just a chore. So I had a look at what other people had done on some of these machine learning papers. And so for that nitpicking textures paper, they actually made their data set available. They machine knit, measured, and photographed around 300 swatches from stitch dictionaries and different patterns. And you can actually download this on GitHub. This is what the images look like. They stretched the heck out of them, though. That was for their method of combining different patch textures together and respecting shape. So I kind of thought that wasn't going to be really appropriate for what I was going to using. It really makes it hard to see the pattern when you stretch them like that. Now, the neural inverse knitting folks, they also made their data set available. So they started out by extracting 12,000 knitting patterns from one of those industrial knitting machines, and they knitted a subset of about 1,000 of them in 5x5 grids. So as I mentioned, knitting is floppy. It's hard to get decent photographs. So what they did is they inserted steel rods into the grid to make them lay flat for taking photos. But they realized pretty quickly this was not going to scale, which is why they moved to simulating the rest with the software simulator. These are some of the examples from the data set, but they're slices of designs. They're not really a single stitch pattern, which is what I wanted. So again, not really appropriate for my purposes. So that left me with sourcing my own data. I'm just a hand knitter though. I don't have access to an industrial knitting machine. I don't have the ability to churn out thousands of samples. But what I do have is a mighty knitting army on Ravelry and on social media. So I thought I'll just crowdsource it directly from knitters, right? So to make things as automated as possible, I started by setting up an email pipeline. And it's kind of not within the scope of this talk to go through this in detail, but the idea is that emails would come in and image attachments would go straight into an S3 bucket, which is our simple storage service. It's object storage. Because I knew that I was going to need them there to run my machine learning training on, and I didn't want to have people emailing me straight to me, and I'd have to download them and upload them and process them. The goal was that I would get hundreds and thousands of images sent in, and they'd just all go straight into the S3 bucket. So once I had this tested and working, I put out the call on social media. This is the tweet I made asking for knitted samples. I decided I was only going to focus on a handful of stitches, 4 of them: stockinette stitch, garter stitch, seed stitch, and moss stitch. These are all just made up of simple knits and purls, and I figured a limited number of classes would make my chances of success a bit better. So I wrote a long blog post about exactly what I was looking for, and more importantly, what I was not looking for. And I shared the email address so that people could start sending in the image. And I put all this on social media, and I put it on Ravelry and a few other places as well. And the good news is it kind of went viral. It got retweeted more than 350 times. And my fangirl moment was I got a reply from Janelle Shea, who some of you might know. She writes those really cool machine learning blog posts where it's like, if a neural network named your cat kind of thing. But yeah, a lot of people were really intrigued by the project. And I started getting images coming through into the bucket. Random human beings around the world are being so helpful and kind and generous. Yay, humanity. But the bad news is that humanity, right? Human beings, all my careful plans got chucked out the window very quickly. So I got several hundred images sent in, but when I went and looked at them, I saw things like this. So some folks sent in pictures of finished garments, which were lovely, but didn't really have the resolution I needed to see a particular stitch pattern. One lovely person on Ravelry, she said, I've sent you several pictures of knitting, but also some Halloween candy because I couldn't figure out how to take it off the email. Okay. Someone on Twitter, people on Twitter would just reply to my tweet with pictures of knitting. And I'm like, no, this is exactly what I was trying to avoid. Someone just sent me a list to a whole bunch of Instagram posts, and I was like, not gonna do that. I got a Calvin and Hobbes cartoon, like sure. And I have no idea what that is in the lower right there. So the first lesson of crowdsourcing is that even with the best of intentions, people are people. I don't mean to shame any of these folks. They were being so generous. They got excited. They were helpful. They didn't read very closely. And crowdsourcing has that as a big risk. But I persevered. So I threw out all the dodgy images and cropped the rest to show just the stitch pattern. And then it was time to get the images labeled. And again, rather than do this all myself, I turned to my army of knitting volunteers. AWS announced a service last year at reInvent called SageMaker Ground Truth, which helps you build really highly accurate data sets for machine learning by coordinating public and private workforces. Basically, it gives you a UI that people can use to label data, and you can use that with your own workforce, or you can even farm it out to Mechanical Turk and have random strangers do it, and you pay them money. So I put out a call for a volunteer knitting task force, and I set up the job to be labeled. And if you haven't seen it before, this is what the ground truth interface looks like. So the volunteer would load a stitch and they'd have a look at it, and then they would pick the correct option from the stitches at the right. And you'll notice I've actually got 6 options there. I've included reverse stockinette because that is the back side of stockinette stitch, and some people sent me pictures of that, so I included it. And also other, which was my catch-all for anything that wasn't one of these 5 stitches. And to minimize the chance of mistakes, I set it up so that every image would have to be reviewed by at least 3 people before it decided what the real label was. And it turns out it was very lucky that I did that because I ran into another problem. Okay, let me just explain here. So on the left, you see garter stitch, which is a very simple knitting pattern where you knit every row. It looks the same on both sides. On the right, you see reverse stockinette stitch, which I mentioned is the back side of stockinette stitch. And they look very similar, don't they? Like they do. In real life, they're super easy to tell apart because one of them is the same on both sides and one of them isn't. And garter stitch, if you slightly stretch it, you can see almost, it kind of makes little ridges. But in a flat photograph, they can be nigh indistinguishable. And I actually found myself having a really hard time telling them apart in the interface, and I know the other labelers did too. So, okay, those labels are gonna be kind of useless. Two of the other stitches I included were moss stitch and seed stitch. And I thought, great, well, these at least are very easy to distinguish, right? See the photos? Totally different, okay? Then I discovered that in British patterns, they use the same words to mean the same thing, the one on the left. Only Americans call the one on the right moss stitch. Well, crap, so there's another two labels that I can't actually trust because everybody's gonna be using different terminology. This is the end result of my labeling job, just shows you just a few of them. So it's got the image and then the label underneath. And so I realized that given that I did not have thousands of images, once I chucked all the bad ones out, and given that I couldn't trust some of my labels, I needed to de-scope even further. So rather than try and identify 5 different classes, let's just identify a single one, right? Have you guys seen Silicon Valley? You know, they build the hot dog or not hot dog app? Yeah, I'm gonna build stockinette or not stockinette. All I'm going for, okay? Let's just solve that one little problem. So time to train the model. There are a lot of ways you can run machine learning algorithms. Data science experts really love Jupyter notebooks. Who loves a Jupyter notebook, right? Yeah? Well, my Python is really rusty, okay, dude? So I decided the easiest thing to do was actually just use the AWS console. I used SageMaker, which has a built-in image classification algorithm. SageMaker is our fully managed service that covers machine learning workflows. So I ran my training jobs on a single P3 instance. Those have powerful GPUs to accelerate machine learning. I gave SageMaker my images in that S3 bucket. As I mentioned, I gave them the labels that my labeling job had output, and I kicked off the job. And it actually took me 7 tries before I got one that actually finished, mostly because every single time I had a configuration option wrong. It's important to read the documentation. I told you I was a newbie at this. Eventually, though, I got one that actually succeeded, and so I really wanted to test it out, right? So to do that, I had to deploy it. Deploying it's actually really easy. SageMaker can give you a method of hosting an endpoint. Just takes a few minutes, so I'm not even gonna show that. So that was the easiest part of the whole project. And then I had to build a web front end so I could show something pretty off to you. And my friend Gabe Hollenby, who's an AWS evangelist in Singapore, he happened to have some code on GitHub that does just that. It's basically a little React web app, allows you to drag in an image and you connect it up to a SageMaker endpoint. The only tricky bit there is that SageMaker endpoints are not public by default, so I had to use a Lambda in between to pass things back and forth. Come see me afterwards if you want to see the details on how that's done. But once that was done, exciting moment, fired up the app, right? Here it is. Cool, let's drag in the first image. Stockinette stitch. It is, in fact, stockinette stitch. Oh my God, I am a machine learning genius. Where is my PhD, right? Like, I'll be speaking at the big conference next year. Cool. I should probably try like one more image, you know, just to be sure. Cool. I'll drag in some garter stitch, right? Well, okay, that's not right. All right. All right. Well, I'll put in something else. This isn't even knitting. This is crochet. Okay. So, clearly something not right. So I had a sort of, really sinking feeling in my stomach. I tried one last ditch example. That's a cat. That's not stocking stitch at all. So no PhD for me. Yeah, it turns out that it is very rare that your machine learning, take some photos of my shame, people. That your machine learning jobs never work out great on the first go. This is what I've been told by people, which is was very good to hear. You never hit the jackpot on the first try. And I went digging in my logs, and I could actually see some stats. This was with only 368 images. My training and validation accuracy were 57% and 45%. This is barely better than a coin flip, yeah. So back to step 3, back to running the model again. So I have since run more than 15 different training jobs, trying to find the magic combination that gave me the best results. So to minimize the effective image size, because I had all different images that people had sent in, I standardized, I cropped every single one down to the same size. I I thought maybe color would be an effect, so I actually stripped them all back to grayscale. I actually then also rotated every image 90 degrees to double my image set, so I had another set of images. I introduced clutter. I added a whole bunch of pictures of like accordions and airplanes and dinosaurs to give more examples of things that weren't knitting. I also ran a hyperparameter tuning job, which sounds really fancy. But basically, hyperparameters are like the little knobs you twiddle for your machine learning job to make it better. And rather than me trying hundreds of attempts at getting it better, SageMaker actually will do that for you. You can set it up and tell it to run, and it will figure out the best combination of hyperparameters to give you the good result. And so I did all that, let SageMaker stir the pile of data for a while, and I got a model out. So let's see what I actually ended up with. Okay. Switch over to mirror. Cool. All right, here you can see I have my machine learning inference app. This is my little React web app. And I have here on the right a whole bunch of pictures. So let's start by dragging in a stockinette stitch. Yay. Stockinette stitch, right? Cool. All right, how about that garter stitch one, the one that it mislabeled that first time? Let's do the garter stitch. It's this one. Remember, that was stockinette before. Not stockinette. Yeah. Woo. Getting there. Hang on. Wait for it. All right, how about a seed stitch? Seed stitch. Not stockinette. Good. Okay. I've got some images of weaving because weaving can kind of look like knitting. And in a few of my tests, these were being flagged as stockinette, so we'll try a weaving. Yes, not stockinette stitch. Now look, it's not perfect. My accuracy is pretty high, but it's not perfect. I'll show you a stockinette that actually fails. So this, is it the second stockinette that usually fails? Yeah, this one. For some reason, this one doesn't read as stockinette, and I have some theories as to why. It's a little bit fuzzy, it's quite close up, but obviously, so it's not a perfect model just yet. And look, I'll even put in your favorite, everyone. I'll put in the cat. Not stockinette stitch. Yes, cool. But one thing I've been doing this week, you might have seen me, is anytime I saw anyone at this conference who was wearing a cool jumper, I actually went and I took a photo of it. So I have some of your jumpers to actually show here. And these ones are in color. You see the other test images I were using were in grayscale, but these are actually in color. So Ben, if Ben is in the room, here's Ben's jumper from the other day. All I've done is crop it down to the right size. Not stockinette stitch, cool. Christian's was interesting. He had a Fair Isle jumper, stockinette stitch, but notice the accuracy. It's 50%, so it really wasn't sure on that one, which is it's kind of a fuzzy picture. It's not the best picture in the world. I was actually really impressed that it even picked that up. Who else? Emmanuel. I'll just drag a bunch in. Lamingus, Jill, Osnad, Paulina, Celia, and me. So of these, let's see, not stockinette, that cable is correct. Oh, I saw that was at breakfast. That was a beautiful cardigan. Stockinette stitch, stockinette stitch, stockinette stitch. This one here, second one in the bottom row, that one was Paulina's. This is really interesting. It's picked it up as stocking stitch, and you can kind of see why. Like if you look at it, it does have that sort of V-shaped repeating pattern, but this is not stockinette stitch. I actually don't know what this is. I have my suspicion that it's like a brioche stitch. I would need to get very close and have a bit of a look at it. So if Pauline is around, I totally want to see this jumper again. But yeah, so that one is one of the examples where it is incorrect, but it's pretty good, right? Okay, let's switch back. So this is the end result of this last training job. So nearly 95%. That's pretty good, considering I am a total newbie at this, and it was a lot harder than I expected it to be. If you're curious, I should mention my total costs for these training jobs was about $25 USD, which is not bad considering how many times I had to do it, how many times I messed it up. But I should mention, you can actually use spot instances for doing your training jobs. That would have reduced my cost by like 70%, but I was too busy just trying to get it to work. So in conclusion, I am not going to be disrupting the knitting industry anytime soon, but the neural inverse knitting people might be. I think between me and them, you may well have a knitting replicator in your house in your lifetime. I should give some thank yous. The dirty little secret of machine learning is that it actually involves a lot of human beings clicking a lot of buttons a lot of times. I had 53 knitters listed here, all of whom sent images to me. If any of them are watching, thank you so much. I had a team of 14 human beings that went through labeling images. I ran multiple labeling jobs. They spent nearly 15 hours labeling 3,000 images. And I also benefited a lot from advice from my colleague, Aparna Elangovan. She's the one who sent me the paper about the people who are solving this problem. And Gabe Hollenby, who, as I mentioned, gave me the front end for actually demoing it to you. So I hope this has inspired you to think about traditional crafts in a new way. Perhaps consider some novel applications for machine learning yourself. I learned a ton doing this project. And if anyone has any questions, happy to answer them. Okay, I have a question on Slido. Ooh, exciting. Are you planning to continue with the other patterns? Yes, I totally am. Now that I know what I'm doing with the machine learning algorithms, I would love to go back and put the other 4 back in. It's just a question of getting accurate training data. Like I said, I need to pick stitches that are actually distinct or take them myself so that I know I can trust the labels. Because when people send them in, they often call things the wrong thing. So yes, I would still love to continue the project. Anybody else? I am not doing crochet anytime soon. Thank you very much.